We are in process to calculate the gradient vector of a sphere. So rather than going through the approach of algebraic equation Cartesian coordinate and traditional multivariate calculus, we have taken path of a spherical coordinate and parametric vector as far as new era in calculus is concerned. So that is the path that we are taking. So rather than calculating through a traditional way, rather than calculating through the traditional way, now we are calculating the gradient vector of a sphere, gradient vector of a sphere through through uh, through a spherical coordinate system and through the parametric vector. So this is what we are seeing. Now, if I have a sphere, if I have a sphere, if I have a sphere, and this is the center of the sphere, and this is vertical, so I have a sphere, and the middle of the sphere, inside the sphere, I have origin, center. Then if this is vertical from the center, then this is radius. Consider this is radius from the center. So this angle is phi. If from center, if this is vertical and this is radius, this angle is phi. If this angle is phi, then the radius component along the vertical is, if radius is a cos phi. Radius component in the on the xy plane is a sin phi. Now depends where the radius is. If radius is in xz plane, if this is x axis and this is y axis and this is z axis, if radius is in xz plane, then a cos phi is vertical, a sin phi is x axis. If radius is in yz plane, then a cos phi is vertical, a sin phi is y axis. Whereas if radius is somewhere else, then a cos phi is vertical, where a sin phi falls on the xy plane at theta degree from the x. So if this is x axis, from x axis theta degree, then that is the another component of this radius. This is one component of this radius, that is a sin phi, and this is one component of the radius, a cos phi. So now if we see the Cartesian coordinate, then we have any point in 3D as x, y, z. Now here any point in 3D in a spherical coordinate system is r, phi and theta. So if this is r or a radius and this is phi, angle with the vertical, then phi is one variable, r is another variable. R can be small, 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 or big, 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 big. So sphere will be bigger. And when r falls on xy plane, then from x axis, what is the theta? So theta can rotate in 2 pi degree. Theta can rotate full 2 pi degree, whereas phi can rotate 0 to 90 to pi. So 0 to pi. Radius can grow from 0 to a. So that is the concept of spherical coordinate system. Now, if I have a function over, if I say f, function over r, phi and theta, then what about df by d phi? This is what we are in calculation. df by d phi, df by d phi. If that is the case, now if I see the actual, the parametric vector, then it is a sin phi cos theta I plus a sin phi sin theta j plus a cos phi k. A sin phi cos theta I plus a sin phi sin theta j plus a cos phi k. So these are the kind of parametric vector. Now if I say df r theta phi by d phi, then it will lead to a cos phi. A sin phi it was in the xy plane. It will lead to a cos phi cos theta I plus a cos phi sin theta j minus a sin phi k. So this is df by d phi. Then we are trying to calculate the gradient. So here we are calculating the gradient where we have kind of with respect differentiation with respect to phi. But anyway, we are now calculating we are differentiating x component, y component and z component. So x component we had earlier, that is x component. What we had earlier is a sine phi cos theta I plus a sine phi sin theta I plus a cos phi k. If I differentiate with phi, then this becomes a cos phi cos theta I plus a cos phi sin theta j minus a sin phi k. Okay. Now I can take out a cos phi. So a cos phi, and inside the braces I have cos theta I plus sin theta j minus a sin phi k. Cos theta I plus sin theta j. So if there is a on xy plane, if it is a here and this is phi, a sin phi falls in xy plane. If a sin phi falls in xy plane, the length is a sin phi. Okay, and direction is a cos theta I plus a sin theta j. I can say this direction as alpha. Then it becomes a cos alpha a cos phi alpha minus a sin phi k. This is what we are seeing. So then if this is xz plane and this is yz plane, then anywhere at theta angle this is alpha z plane. This is xz plane where the theta is variable, where phi is variable and theta is 0. This is yz plane where the phi is variable and theta is 90 degree. For any theta, this is alpha z plane where alpha is a cos theta I plus a sin theta j. Okay, so finally we have kind of uh, uh, we have gradient vector, and x component of gradient vector is a a cos phi cos theta I, and y component of gradient vector is a cos phi sin theta j sin theta, and z component of gradient vector is minus a cos minus a sin phi. So this is the new gradient coordinate that we are seeing. What it is exactly? So we kind of shrunk the uh, the cos theta I plus sin theta j as alpha. Then it comes as a cos phi alpha minus a sin phi minus a sin phi k. Okay, so now if I consider this plane, that is alpha z plane, this is a new plane, and then we calculate when we see the gradient vector. First we will see the position vector. So this is what we are seeing. So if this is center of the sphere and the sphere is all around, if this is center of sphere, then any point its alpha component, any point its alpha component is a sin phi, whereas vertical component is a cos phi. Now the gradient vector is a cos phi, and vertical component is minus a sin phi. If I do dot product, it becomes 0. So first is a sin phi along alpha and a cos phi along k. So if this is center, then it is radial everywhere. If I take any point where the alpha component is a sin phi and vertical component is a cos phi, then that point to center, it is a radial. It is a radial. Radial in all direction from the origin, from the center. So it is a kind of radial everywhere. Okay, everywhere it is radial. If this is radial, then the gradient vector is perpendicular to the radial. So it is tangential. So if this is a sphere, then this is radial everywhere, that is the points, but it is tangential everywhere as far as gradient vector is concerned. If this is radial, perpendicular to is this, but as I stated, but perpendicular to this is come in anywhere in this plane. So which one is a perpendicular to this? Which one we try to find out? That is in alpha z plane. So if I am at theta, if it theta is 0, then it is like this. Here it is parallel to x-axis, and here slowly it will become parallel to z-axis. So this is the kind of gradient vector that we see in xz plane. If theta, if this is x-axis and this is theta, then this is alpha z plane. If this is x-axis, this is theta, then if theta is 90 degree, then we are in yz plane. If we are in yz plane and this is the position vector, that is radial, that if this is the end of the sphere, then the gradient is tangent to the sphere. So gradient will move like this as a tangent. Okay. So this is how it is. So if this is a sphere, okay, so if this is a sphere, okay, so if this is a sphere, then this is radial everywhere. This is position vector, whereas this is tangent and this is the gradient vector that is vertical to the position. So this is the tangent vector. Now, if we are in xz plane, the tangent vector will be like this. If we are in yz plane, then tangent vector will be like this. If we are in any alpha z plane where there is some theta, then that if this is x plane, x axis, this is theta, then it will be in alpha z plane. So this is the kind of gradient vector that we are seeing. Okay, x component we calculated the derivative along with the phi, y component with the phi, and z component with the phi. What about if I want the variation with theta, where the radius and phi are constant? Here, when we can differentiate it with the phi, we consider that it is constant, radius is constant and theta is constant. At particular theta and particular radius, with differentiation with phi, how much it should be. Now, if I keep radius and phi as constant, then if I differentiate it, then the x component, that is a sine phi cos theta, would become minus a sine phi sine theta I, plus a sine phi cos theta j, plus 0, because a cos phi does not have anything in theta. So variation, for if I see variation with theta, so theta is a xy plane. So if this is a sphere, then if I want to we can see this black line, this black line. So this black line is a kind of xy plane. So with variation in the height, we can cut as a contour. So now we have kind of so many circles. If I just see xy plane, then at the center the xy plane is the biggest. Then if I go up, the xy plane becomes smaller, smaller. There is a circle. So if I chop this, if I chop this along the horizontal, if I chop this along the horizontal, so at the center there will be a circle if I see from top. So top view is a circle. That circle will start reducing in the size, and at the top the circle is negligible, it's not there. Now, now we have considered as r as a constant, r as a constant and phi as a constant at a particular phi. If phi is something, then at this phi it would rotate like this as far as theta rotation is concerned. If phi is 90 degree, then it would rotate to this full strength in the xy plane. If phi is 180 degree, then there is nothing. If phi is 0, there is nothing. If phi is something, then it would rotate like this. That area, that area is a circle that is at angle phi, and then the radius is a sine phi. Okay, so if this is vertical and this is phi and this is a sine phi, e is its component on the xy plane, and then it is phi. Then if I want to rotate in xy plane, it would rotate like this. If phi is 90 degree, then it would rotate with the full maximum area. Now, if I calculate the gradient vector along when theta is varying, then it is a sine phi minus sine theta I plus a sine phi cos theta j plus 0, because a cos phi k differentiation with theta was 0. So only in the xy plane the gradient exists. If that is the case, then earlier the xy plane was a sine phi cos theta I plus a sine phi sine theta j. Now it is a sine phi minus sine theta I plus a sine phi cos theta j. If I do the dot product, then it becomes 0. So in the xy plane itself, so xy plane if I see, then the position vector is radial. So velocity vector or gradient vector, since it is perpendicular position vector, then it will be tangential like this. But it will be only in the xy plane. It won't have any component along the z axis. So at the center, if this at the if this if I if this black line, if I cut it along the x-axis, if we cut horizontally, there is xy plane. In the xy plane, the circle is like this, where this is the position vector. It is radial to the center. If this is center, if this is center, then it is radial to the center. If this is position vector, then the velocity or gradient vector is perpendicular to it. Then it is then it is tangential. If this is position vector in the xy plane, then gradient vector is tangential. So tangentially it would rotate like this in xy plane. So tangentially it would rotate in the xy plane. Okay, like this. It will go like this. Okay, whereas position vector is from the center, it emanates, it comes out like this. Okay, it is perpendicular. So we saw variation with phi, where theta and r is constant. Then if this is the case, then for any phi it would go where it has vertical component. This is the gradient vector, whereas this is the radian. But if I keep phi and r constant, then theta, for theta at any phi, if phi is here, then theta, consider phi is 90 degree, then the radial vector would go in a xy plane only. Then the gradient vector would go in xy plane only. Okay, so that is the scenario. Now let's keep theta and phi constant and differentiate only with a or r. So the if initial function was f r theta phi, then dr by df by dr. If that is the case, then from the first, that is r sine phi cos theta or a sine phi cos theta, it will become sine phi cos theta I plus sine phi sine theta j plus cos phi k. A will go off everywhere if I differentiate with R. What we are getting is, so if this is the radius and phi is constant and theta is constant, radius is growing from 0 to this level. So sphere is bigger. If sphere, if radius is becoming bigger, if there is a rate of change in radius, if there is a unit change in radius, how many unit change will come in vertical, how many unit change will be seen in x-axis, and how many unit change will be seen along the y-axis. This is what actually we are seeing. So if I am saying k component would vary with the cos phi, then means if there is 1 unit of change in radius I am bringing, then there is a cos phi unit of change that will be seen in the vertical side. That is the gradient vector, whatever you consider. If there is a unit change of radius, then there is a sine phi cos theta, that much change that will be seen in the x-axis. If there is unit change in the radius, then sine phi sine theta, that will be seen along the y-axis. So that is the gradient. So x component would change as sine phi cos theta, y component would change as sine phi sine theta, and vertical component would change as cos phi when there is a unit change that we see along the radius. So radius from 0 to, if I bring it to a, then per unit change, if I keep changing this much change, it would be seen along the x, y and z axis. Okay, now you can think about the direction, and direction looks like it is not changing because we are not changing angle anyway. Earlier it was a sine phi cos theta, a sine phi sine theta, a cos phi. Now a has gone. Now it is sine phi cos theta, sine phi sine theta, and cos phi. If that is true, then the gradient vector direction is along the position vector or radial only. If this is a sphere and this is radial everywhere, then gradient vector is along the radius only. That is what we have been seeing, that the kind of position vector and velocity vector both are in same direction as far as parametric equation is concerned if it is a line. If it is a curve, then it is tangential. If it is not a curve, then it is along the line. So now we have gradient vector of x along the x, y, z axis when only phi is variable, and when only phi is variable and r and theta or a and theta are constant, and that we saw that comes as a a a cos phi cos theta I plus a cos phi sin theta j minus a sin phi k. If there is variation in theta and phi and r are constant, then it comes as a a a sin phi minus sin theta I plus a sin phi cos theta j plus 0. If there is variation only in the radius side where phi and theta are constant, in that fashion it will become a will go off from everywhere. So it will become sine phi cos theta I plus sine phi sin theta j plus cos phi k. So we have, if f is the function over r phi and theta, then df by d phi df by d theta and df by dr that we have calculated. Now, can we say that what would be the actual gradient vectors x, y and z component when we have variation in phi, theta and r all three? So, parametric vector is anyway, it's a matter of research and especially the multivariate. So, if we are saying that I have variation that is seen in phi, theta and r, then what would be the gradient vector as far as all three variations are concerned? Then probably we have to add x, y, z components separately. Like if I say x component with the variation of phi is a cos phi cos theta, a cos phi cos theta. Then variation with theta is a sin phi minus sin theta, and variation with r is sin theta cos phi. Then we have to add all three components. So it will become a cos phi cos theta plus a sin phi minus sin theta plus sin phi cos theta. So this will become, all three become the x component of the gradient vector as far as all three component variation, all three component in the spherical coordinate system variation is concerned. Similarly, we can calculate for the y. So now we are talking about df by d phi, df by dr, and df by d theta, three all together. So if I see the y component, then it will become y cos phi sine theta plus y, I mean a sine phi, y component is a sine phi cos theta plus a cos phi, sorry, a, first with the phi we have to differentiate, so it will become a cos phi sine theta plus a sine phi cos theta plus a sine phi sine theta. That is the y component. Now as far as z component is concerned, then it is minus a sine phi, minus a sine phi plus 0 plus plus cos phi. So this is the kind of gradient vector as far as all three components of the spherical coordinate system variation is concerned. Okay, so not difficult. What we get with the spherical coordinate as far as the gradient, as far as the parametric vector is concerned? What we get is that clean cut direction. So we know the position vector relate, position vector, coordinate vector, direction, and then we instantly know the all other directions like the gradient vector direction with, when we kind of keep theta and r constant, uh, phi and r constant, and then phi and theta constant. Someone can now estimate what would be the gradient vector direction when we have all three variables. So we have to calculate the value, and that value we have to draw as a position vector at that point, the point, the r phi theta, the point we are taking on the sphere. So in this sphere, every point is r phi theta. So at particular r phi theta, if I calculate x, y, z component, and then we have to see its position vector, where it is pointing, that is the direction of the gradient vector when all three components of the spherical coordinate system, they vary. Okay, so idea was that we have taken a sphere. So sphere is x square plus y square plus z square equal to r square as far as a spherical coordinate system in Cartesian coordinate system. As far as a sphere equation for the Cartesian coordinate system is concerned. So x square plus y square plus z square and equal to r square. So that is the kind of algebraic equation. If I consider fxyz equal to x square plus y square plus z square, then its gradient vector would be 2xi plus 2yj plus 2zk. So gradient vector in Cartesian coordinate, its coordinate would be 2x, 2y, 2z. So that gradient vector in Cartesian coordinate, that we'll see in future. So now we have calculated gradient vector as far as 3D sphere is concerned. What about 2D is 2D circle, 3D sphere? Then equivalent in of the 3D sphere is 2D circle. If 2D circle is there, okay, if there is, if there is, if there is 2D circle, if there is 2D circle, then this is, if there is 2D circle, then this is exact, then this sphere, if I chop along x-axis, then I keep getting 2D circle. So this is, this is 2D circle. So if this circle, if I start restricting it along vertical and start restricting it along vertical in up and down, it will become a sphere. So this is a cross section, one contour of 2D circle. So the equation of 2D circle is equation of 2D circle would be kind of a sine ti plus a cos tj, where t is the angle in the radian. So this is parametric vector. If you see the sphere we had taken in the variation of phi, theta and r, but that is not the exact example of the parametric vector, where x component was a sine phi cos theta I, a sine phi sine theta j and a cos phi k. So the best way is to be only one independent component, that is t. Okay, if I do everything, then why what you would do? So the spherical equation, that is x square plus y square plus z square equal to r square or a square, that is in Cartesian coordinate equivalent is r sine phi cos theta I plus r sine phi sine theta j plus r cos phi k. Now, bringing it to only in variation of t is a kind of tough task. Probably it may not be possible also. That we will see. So, we did in variation of three component r, phi and theta. But the best solution as far as parametric equation is concerned, parametric vector is concerned, that the f r phi theta should be converted to RT, where now the all r phi theta will go away and everything would come x component, that is fx, that means ft will come in the function of t, y component, that is g function, that will come in, that will become gt and in function of t, and z component, that is kh fgh ht, that is a function over independent component t, will become ht. So that may be not be possible and it has to be, that is the exact gradient. Now if I am 2D, then equation is a cos ti plus a sin tj. This is exact parametric equation where the x and y component ft and gt are in function of t1. Now if I try to, if this function is rt, then dr by dt is the gradient vector or velocity vector or vector field. So that will come as a cos ti minus a cos, sorry, a minus a sin ti plus a cos tj. If I do the dot product of position and velocity vector, it comes as 0. So if if the position vector or the distance, what we are saying, if position vector from the center is radial, if I take any point, if t is 0, then a cos ti plus a sin tj, only a cos t, that is a, along x axis would exist. If t is pi by 2, then only sin t, the y axis will exist. So it is radial. Can we see? It is radial. So this is the displacement vector. If I calculate the velocity, it is perpendicular to it. So it will be tangential along the circle. So this is how the gradient vector. So gradient vector equation is minus a sin t I plus a cos t j. So if you see, if you draw the position vector of this at any point here, so at any point that is in variation of a and t, angle and radius, then position vector would be like this. Okay, that is the 10. This is how vector is drawn. So if you take any point from the center, that point, whatever the direction you are seeing, that vector you have to just shift there. So it is like this. You have to shift here. Then this, it will become like this. So in 2D, the velocity vector is for a circle, it is tangential. Now let's take case of parabola. So parabola in 2D is y equal to kx square, where k is some component, constant. So if this is y axis and this is z axis, then this is parabola. I hope this is visible. Then this is parabola. If this is parabola, then y equal to x square. If I keep increasing x, then y would increase, then square. So y equal to kx square, where k is constant, so that we can control the way the slope is. So y equal to kx square. If that is true, then its parametric equation would be ti plus k t square j. That is the parametric equation. If it is passing through origin, then ti plus k t square j. So this is the equation of parabola. Now if I calculate, so can you see the now the position vector? If I am at 0, if I am at origin, if this is the origin, if this is the origin, if I am at 0, if this is the origin, then as we go along, then it is rising sharply. Now if I calculate, when x is 10, then it is 10i and k is 1. Then it is 10i plus 100j. If it is 100i, then 100i plus 10,000, I believe 10,000 j. So when x is 1, then y is 1. When if I take the parabola, when x is 0, at that time x when the t is 0, then the kind of the position, it is a vector is at origin only. There is no kind of position vector. It is 0 along x axis and along the y axis. 0i plus 0j. Now, if it is 1 and 1, if t is 1, then y-axis component is also 1. Okay. Then it is 45 degree. It is like 45. So if parabola is like going like this, parabola is going like this, then at 1, 1, so it starts like, then at, it starts from 0, there is no direction. At 1, 1, it is like this. If it is 2, then 2, 4. Then slowly it will start becoming like this, and it will become almost vertical if we go far in the x. So this is the position vector. So if I draw from origin, then it will be, initially it will be like this, and it will become vertical. So this is the position vector. It is like this. It is like this. Okay. Now we'll calculate the gradient vector. So it will become as I plus k 2k t, or if k is 1, then 2t. T square derivative is 2t. So ti plus t square j, if I calculate the gradient vector, then x component is 1 and y component is 2t. So if this is position vector, the position vector slope is position vector is t and t square. Then the velocity vector is 1 and t. 1. So x component is always 1. X component is always 1. So now if I calculate the gradient vector at 0, then x component is always 1. So at 0, 0, if this is the, oops, 1, if this is the, if this is the parabola, if this is the parabola, then if this is the origin, then at origin the gradient vector is like this. I, so t I plus t square j, so 1 I plus 2 tk. If t is 0, then still x component is there. So it starts like this, the gradient vector, that is the tangential looks like, then it will become like this, then slowly it will also become like this. But the vertical and horizontal, if I take the of the vector, then it is ty1, it is t. Whereas there, in that sense, the variation in the vertical was square. So if I am taking as a kind of 10, horizontal is 10 and is uh, vertical becomes 100 and horizontal is 10. This is the kind of uh, position vector. Whereas now if I take as 10, if I take as 10, then vertical is 10 and horizontal is 1. If I take 1000, then vertical is 1000 and horizontal is 1. Okay. So the gradient vector would not vary in the x component, it would vary only in the y component. whereas the position vector varies in both directions. Obviously, these are not perpendicular to each other. Means if I have ti plus t square j and I plus 2tj, then certainly they are not perpendicular. If I do dot product, they may not become 0. This is how it is. So we calculated the gradient vector for the sphere, circle, and gradient vector for the parabola as far as 2D is concerned. What about gradient vector of the paraboloid? 3D. Okay. Now, if I have a parabola, I really have a paraboloid. I have shown it. Like this is the typical case of the parabola. So this is center, this is origin, and it goes like this, and in all direction it goes like that one. Very heavy. So this is the paraboloid. If this is the paraboloid, then what is the equation of paraboloid? Fxy equal to x square plus y. So if I consider the converting it to the parametric vector, then it will become in a Cartesian coordinate, it will become 2xi plus 2yj. 2xi plus 2yj. If I calculate kind of both, if I place the z also, then it would become x square plus y square minus z equal to some constant. So fxyz would be x square plus y square minus z. So then in 3D, the gradient vector would be 2x, 2y and minus 1. But anyway, if I calculate the surface equation also, then fxy equal to x square plus y square. That is the 3D equation for the paraboloid. So gradient vector will be 2xi plus 2yj. Now calculating back it to, if I consider gradient vector is like if I have a parametric vector is rt and dr by dt is the gradient vector, that is 2xi plus 2yj, then from 2xy and 2yj bringing back the x and y component of parametric vector is impossible. Means if I do x dt to bring the x component of the parametric vector and then 2x dt and 2y dt to bring the 2y dt and integration here 2x dt integration to bring the x and y component of the parametric vector is impossible, because we are integrating with the in a variation of dt where the dependent component function is x. Both are not related to each other. If that is the case, then certainly we cannot do. So we may go for Euler estimation to get the sum point. So these are the area where we need more research. So if I get to do research and find out, then probably I can let you know. So parabola in 2D plane that we saw, if y equal to x square, then it is ti plus y equal to kx square, then ti plus kt square ki plus 2 ki plus kt square j. That is the parabola equation in 2D. But if it is z equal to x square plus y square, then first we have to calculate the, to get the parametric vector, first we calculate the vector field, that is 2xi plus 2yj. Now each component, that is f1 and f2 component, that is 2x and 2y, we have to integrate with dt to get the x and y component of the parametric vector. So 2x dt integration and 2y dt integration is not possible. So probably Euler estimation would give some point as far as parametric vector is concerned. Otherwise, as a algebraic function that we see in parametric vector, it is not possible. So someone can calculate it. But anyway, so this is what is the calculation of the gradient vector as far as parametric vector is concerned. What we'll see now as an algebraic equation and then algebraic equation and Cartesian coordinate. Very interesting. Very interesting. That is what is going on. So that we will see, and how gradient vector looks little funny when we compare with the parametric vector. So that we will see.